When wind speeds push past 30 meters per second and temperatures drop to minus 40 degrees Celsius, people can barely stay on their feet. And yet, some teams still manage to finish major projects on schedule in conditions like that. This top 10 list shows great engineering completed under truly extreme environments. Number 10. Svalbard Global Seed Vault. When you see this place, it looks like the entrance to a science fiction film. But do not rush to take a photo. Norway built it on the Svalbard archipelago inside the Arctic Circle as a backup for humanity, a secure reserve of crop seeds from around the world. In a food disaster, it can become a last line of support for global food security. It does not try to reach the sky, it goes straight into the mountain. The access tunnel runs about 120 meters inward, and the target temperature is locked at minus 18 degrees Celsius. Outside you have polar night, snow, and roads that can vanish under storms. Inside you have a sleep chamber for seeds. Even if refrigeration fails, the design tries to let permafrost slow down the temperature rise. One key moment happened around 2016, when unusual warming led to meltwater entering the entrance tunnel and freezing. The seeds were not damaged, but it made one reality impossible to ignore. Even the Arctic can thaw. The upgrade plan after that was blunt and practical. Better waterproofing, better drainage, redundant power, redundant cooling, and a redesign that treated the worst case as a design input instead of a surprise. Number 9. IceCube Neutrino Observatory. This is not a decoration in Antarctica. Scientists wanted to use the cleanest and most stable ice on Earth as the detection medium to catch particles that almost never interact with matter, neutrinos. So the construction method was unusual, using hot water drilling to melt deep shafts into the ice sheet. The drilling rate reached close to 2 meters, per minute. Then sensors were lowered step by step down to about 2,450 meters. The full array includes 86 sensor strings, and the work could only surge forward during the Antarctic summer window, roughly from November to February. Picture the scene: deep cold, strong wind, a hot water drill running, hoses shaking like a living thing, and a whole wall that can refreeze and close. IceCube showed discipline by turning the work into a tight pipeline: drill, deploy, calibrate, seal, with no wasted gaps. The team treated extreme cold as a process variable, not background scenery. The project finished in 2010 with a cost around $279 million. It was expensive, but it proved something else. Even the harshest place on Earth can be engineered into a workable job site. Number 8. Confederation Bridge. This bridge links Prince Edward Island and New Brunswick in Canada, a true lifeline for the region. Before it, travel depended on ferries, and in winter, ice and wind could make crossings miserable or impossible. The bridge runs 12.9 kilometers across a strait that freezes. So the most serious threat is not waves, it is ice. Ice is not a pretty layer. It moves, it crushes, it forms pressure ridges, and it can push like a slow bulldozer. The answer is simple in principle: prevent ice from delivering a concentrated hit to critical parts. The piers were shaped to split ice and spread loads. Like the bow of an icebreaker, instead of a direct slam, ice is forced to fracture and flow around the pier. Construction strategy was just as deliberate: build major components onshore, ship them out during the right windows, and minimize exposed work in rough seas. The bridge opened in 1997, with a cost around 1.3 billion Canadian dollars. The win is not length, it is denying ice the chance to focus its power. Number 7. Russky Bridge. In Vladivostok, Russia built this bridge around 2012 to connect Russky Island, aligned with a major event schedule and a fast development push. The strait is brutal: strong winds, heavy seas, and winter ice. Public data puts local temperatures from -31 degrees Celsius to +37 degrees Celsius, and winter ice thickness can reach about 70 centimeters. The headline stats are impressive, a main span of 1,104 meters. But the real difficulty is operational discipline. At wind speeds around 36 meters per second and wave heights near 6 meters, can you lift and install anything safely? Once conditions cross safety limits, you stop immediately, lock down equipment, and pull people out. On monitoring footage, tower cranes can look like they are being dragged by an unseen hand, and guy lines can sing under load. To avoid gambling, the team broke work into smaller units. Anything that could be done on site was done on site. Anything that could not be done safely in that exposure was prefabricated, while parallel tasks like cable inspection and saddle and anchorage preparation ran to shrink the time spent in the danger zone. In this kind of environment, the most important skill can be said in 2 words: knowing when to stop. Number 6. Hong Kong-Zhuhai-Macau Bridge. This is the megalink that ties Hong Kong, Zhuhai, and Macau together, a project built because the Pearl River Delta had a hard transportation need. It is not just a bridge, it is a 55-kilometer bridge island tunnel system. From day one, it faced the reality of the South China Sea, frequent typhoons, complex marine conditions. The design standard is strict, a 120-year service life, with extreme boundary cases baked in, including typhoon-level winds and major earthquakes. If you want the how, focus on the offshore strategy. First, move critical work into controlled environments. Mass prefabrication in factories and dry docks instead of improvising at sea. Second, a typhoon response mode. Once warnings arrive, a checklist takes over: vessel withdrawal, reinforcement, sealing, reinspection, and more. Third, immersed tube tunneling, with a mindset of stabilizing massive elements first, then lowering and connecting to reduce long exposure time in open water. The clearest drama is managerial. Every time a tropical cyclone approaches, you can see planning and nature collide in real time. Number 5. Trans-Alaska Pipeline System. In the 1970s, the United States built a giant energy corridor to move oil from the North Slope down to a southern port. It crosses Alaskan wilderness, where logistics are extreme. The job was not just build a line, it had to cross widespread permafrost and a major earthquake zone. The iconic image is familiar: endless snowfields, bright white glare, a dark pipeline stretching like a long serpent. Lifted on supports, raising the pipe was not for style. It was a stability requirement. Hot oil would thaw permafrost, and if the ground settled, the pipe could twist and rupture. So large sections were elevated, with added measures to stabilize foundations and solve transport in remote terrain. The human cost was real. Public records report 32 workers and contractors died during construction. Extreme work is not a mood. It is a campaign where every link is treated like a fight, including the basic problem of getting machines to the line, which sometimes meant building the access route first. Number 4. Berkut Offshore Platform. This is the category of huge capital, harsh seas, and especially brutal winters. The design targets show the scale of the problem. -44 degrees Celsius, 18-meter waves, 2-meter thick sea ice. It is like fighting a moving field of ice with a giant hammer. Sea ice is not a static load. It drifts, it crushes, it hits in cycles, and it can wear through outer shells and damage lines. The response is straightforward, but serious. A very thick protective outer layer, critical components tucked inward, and vulnerable piping moved inside the structural shell, so ice impacts meet armor first. Offshore work windows are short, and when weather turns, ships cannot sail, lifts stop, and the schedule must be rewritten. The real capability here is turning uncontrolled ocean conditions into controlled modular assembly. Number 3. Qinghai-Tibet Railway. The site challenge came in 3 layers: low oxygen, permafrost, and high-altitude cold. The highest point is near Tungula Pass at about 5,072 meters. More severe, over 80% of the Golmud to Lhasa segment, more than 960 kilometers. Sits above 4,000 meters. Public data puts permafrost sections around 550 kilometers. That means workers had to operate in cold while their bodies struggled to breathe. For people, oxygen supply, rotation schedules, and medical support are not optional. For permafrost, which is extremely sensitive to heat disturbance, the solution combined embankments, bridges, ventilation, and insulation to reduce thaw, settlement, and deformation. The defining image is not a stunt. It is workers tying rebar while wearing oxygen masks, because that is what survival looks like. Number 2. IHNC Lake Borgne Storm Surge Barrier in New Orleans. After Hurricane Katrina, New Orleans upgraded its flood protection system on a massive scale. This barrier is a key part of keeping storm surge out of city waterways. It runs about 1.8 miles. Construction moved from 2008 to 2013, with a cost around $1.1 billion. It was already operating by 2012 and helped block storm surge during Hurricane Isaac. The details matter because it is not just a wall, it is a heavy infrastructure system. Public data reports 1271 primary concrete piles, with pile diameters around 66 inches and lengths around 9 times 44 feet, plus angled steel pile systems behind, for added stability. Construction planning also matched local climate reality. During hurricane season, the schedule behaves like a countdown. When warnings appear, the site goes into shutdown mode. Evacuate equipment, secure temporary works, close critical routes, and accept delays rather than gamble. Number 1. Amundsen-Scott South Pole Station. This is a year-round research base at the geographic South Pole, one of the most extreme long-term human outposts on Earth. The old station gradually disappeared under accumulating snow. So the new station followed a clear idea: raise the whole building on an elevated structure that can be lifted over time. To resist the way snow buries everything year after year, the new station was completed and entered service around 2008. The construction season is short. Miss the window and you wait a full year. Materials depend on a logistics chain of airlift and staged transport. The environment is severe. Even in summer it is cold. And winter temperatures fall into ranges that do not support normal human life. The design logic can be summarized in 3 points: elevated structure, redundancy, and maintainability. Modular elements allow replacement. Life support systems, power, heat, water must run independently through isolation in winter. The hardest part is the one you care about most. In a place where the next chance is a year away, every bolt feels like a contract with legal force. Install it wrong now, and the fix might not arrive until next year. So the real satisfaction of extreme engineering is not raw scale. It is the way these projects break nature into actionable rules. What kind of extreme environment do you want next? 50 degrees Celsius desert heat, volcanic ash zones, active fault lines, or deep ocean high pressure? Drop the environment you want most in the comments. And the next episode will build a top 10 list that pushes even further.